It's good to see everybody. I can't physically see. I wish we were all in the same room, but I'm joining you from Provo, Utah. I'm sure all of you are gathered from around the world, and we want to welcome you. I'd like to, on behalf of my fellow program chairs, Christian, Laura, and Jingyi, I want to thank all three of them for their hard work throughout this last 6+ months through the reviewing process. I also want to thank Gerard and Kevin for their leadership. So I'd like to share with you a few things about our program this year. We had more than 1,200 submissions, 1,148 of which were fully reviewed. As many of you know, WACV is a 2-round review process. Our first round submissions totaled 397, the second round 844. And this was up from about 1,096, so about 20% increase, not quite that since last year. We accepted 406 papers, about a 35% acceptance rate. And as Kevin mentioned, we have 614 attendees at the conference this year. We look forward to hopefully having many of you back next year when we're actually in person, where we wish we were. I should have worn my Hawaiian shirt. I like Kevin. Thanks for doing that. In order to facilitate this reviewing process, we had 67 area chairs, 15 of whom were women, and we had area chairs spread pretty evenly across the three major continents where we have vision researchers. We hope to get even broader participation in our area chair panel next year. A pretty good mix of senior and early career researchers. 17 of our area chairs were from industry and the balance from academia. I want to thank all of the area chairs. Quickly, I'm not going to read through them, of course, but we want to thank all 67 of our area chairs for their efforts. We had 1,948 reviewers who ended up completing reviews. We actually had a handful more than that who were willing to review for us, but due to the paper matching, not everybody received assignments. But these reviewers, many of them helped for both of our submission rounds and reviewed up to 6 papers. And so we want to, if we were all together, we'd give a round of applause for all of our reviewers. We really couldn't put on the conference without the effort of so many reviewers. I want to thank you for your expertise and your time. So with that, we're going to begin the awards session. We have 5 awards that we're going to present, but I want to first thank our awards committee. The awards committee was chaired by Margaret Betke and consisted of Tina Tutliars, Michael S. Brown, Scott McCloskey, and Terry Bolt. A number of them have served in other capacities this year. But the awards committee were given 15 papers that were recommended by the reviewers themselves and also the area chairs. And the awards committee took these 15 papers and selected 5 awards. The 5 awards that we're going to give right now. I'll announce them now, and then we're going to have a short 7-8 minute presentations from each of the award-winning papers. So the awards that were given were, because WACV is a applications-focused conference, we have 2 awards, one for an algorithms paper and one for an applications paper. So best paper in each of those categories. The best student paper, best paper authored by first author who's a student, and then an honorable mention both for best paper and for best student paper. So the best paper algorithms was Deep CSR, a 3D deep learning approach for cortical surface reconstruction by Rodrigo Santa Cruz, Leo Lebrat, Pierrick Bourget, Clinton Fuchs, Jürgen Fripp, and Olivier Salvado. I apologize if I'm not pronouncing your names correctly. Rodrigo will be giving that talk in just a moment. The best paper for applications goes to 3D human pose and shape estimation through collaborative learning and multi-view model fitting. And the authors are Zhongguo Li, Magnus Oscarsson, and Anders Hayden. And Zhongguo will be giving that talk. The best student paper award is given to a pose proposal and refinement network for better 6D object pose estimation by Ameni Trabelsi, Mohammed Shaban, Nathaniel Blanchard, and Ross Beveridge. And Ameni will be giving this talk. The best paper honorable mention goes to generative patch priors for practical compressive image recovery by Rushil, Anirudh, Suhas Lohit, and Pavan Turaga. And Rushil will be giving that talk. The best student paper, honorable mention, goes to Meta Module Network for Compositional Visual Reasoning by Wenhu Chen, Ji Gan, Linji Li, Yu Chang, William Wong, and Jinjing Liu. And Wenhu will be giving the talk for that one. So without further ado, I'm going to turn the time over to Rodrigo for presenting the best paper algorithms award-winning paper, Deep CSR.
Okay, now it's on mute. Hi everyone. I'd like to thank the organizers for the award and also for the invitation. And today I'm going to present the Deep CSR 3D deep learning approach for cortical surface reconstruction. Okay, cortical surface reconstruction is a well-known task in medical imaging, and it plays a central role in the study of neurodegenerative diseases like Alzheimer's and Parkinson. The goal is basically to estimate triangular meshes for the inner and outer cortical surfaces, which defines the brain cortex. And this inference has to be done from MRI. Basically, the inner surface is the boundary between the brain white matter tissue and the gray matter tissue, here in red in this diagram, while the outer surface is the boundary between the gray matter tissue and the CSF, here in blue. As exemplified by this diagram, this is a very challenging problem, since these surfaces are continuous objects that cut the MRI voxels in different patterns. Therefore, subvoxel precision is required to reconstruct well these surfaces. Existing methods and Deep CSR. Traditionally, this problem is tackled by lengthy pipelines of imaging process techniques, like the widely used FreeSurfer and its recent fast and deep learning version FastSurfer. Both of them first voxel-wise segment the input MRI and then fit surfaces within the voxels in the boundaries of the tissue classes. While simple, this approach is limited by the resolution of the input MRI, in which it is hard to capture the high-frequency details of narrow continuous objects, like the cortical foldings in the cortical surfaces. To overcome this problem, and inspired by new developments in 3D object reconstruction, like occupancy networks and deep SDF, we propose Deep CSR, a 3D deep learning model that learns to predict implicit surface representations for cortical surfaces directly from the MRI. Let's have a look how it works. From a dataset of pairs of MRI and target surfaces, represented as a triangular mesh and computed offline with traditional methods, we first compute an implicit representation of this surface by densely sampling points around it and compute the occupancy field or the sign and distance function of these points in relation to the target surface. More specifically, given a sampled point, the occupancy field assigns a binary value indicating whether this point is inside or outside of the target surface, while the sign and distance function goes further and also assigns the sign and distance from this point to the target surface. Once we have this data, we train a neural network to map from an image and a point in real coordinates to its implicit surface representation, which could be occupancy field or sign distance function. Once this model is learned, we use this network to predict implicit surface representation for new MRIs. More specifically, given a new MRI, we sample equidistant points in the brain template and pass their coordinates to the network to obtain the implicit surface representation of the target surface. Note that we can reach a very high resolution by just predicting implicit representation for more and more sampled points. Finally, with the predicted implicit surface representation at the desired resolution, we can run a topology correction algorithm and a isosurface extraction method to reconstruct the target surface as a triangular mesh of spherical topology. An important detail in the architecture of AI networks is how to extract features from the input image to predict the implicit surface representation for a given point. From MRI represented as a grid of voxels and a point represented by its real coordinates, we first compute feature maps by applying 3D convolutions to the input MRI. Then we map the input point to the image and its respective feature maps, where feature values are interpolated and concatenated to form a feature vector aggregating local and global information to predict an implicit surface representation for the given point. Finally, this vector named here hypercolumn and the point coordinates are passed to a decoder, which outputs the implicit surface representation for this point according to the input image. We show later in our experiment that this feature extraction approach is essential to reconstruct high-frequency details like the cortical foldings. In our experiments, we compare our approach to FreeSurfer and FastSurfer frameworks. First, we evaluate the precision or reproducibility of these algorithms in a test-retest experiments where the same individual is scanned twice in a short time interval, and the goal is to recover identical surfaces, even with the variations in the MRI acquisition. Second, we evaluate the accuracy of these methods by comparing the mesh-based segmentations for the brain cortex itself with manual segmented data using the multi-atlas labeling challenge dataset. Finally, we compare the runtime by reporting the average reconstruction time for a given input MRI. Our result shows that DeepCSR is more precise, providing 90.9% error reduction compared to FreeSurfer and 5.4% compared to 5.5% compared to FastSurfer. It's also slightly more accurate and much faster than these competitors. It's on average 13 times faster than FreeSurfer and presents 90% less runtime variation across subjects than the FastSurfer. I also like to highlight that almost 6% of the DeepCSR inference time is spent in the topology correction post-processing step, which can be improved using more modern techniques. We also empirically analyzed some modern decisions taken in the development of DeepCSR using 3D deep learning metrics between the generated surface and the pseudo-ground truth ones. First, we noted that sign distance function is more suitable for this problem than the occupancy field, since it more accurately defines the target surface. Second, when representing cortical surface as implicit surfaces, densely sample points near the surface is better than uniformly sampling points in the bounding box around it. And last, hypercolumn features and predicting implicit surface at a high resolution is key to capture the high frequency details in the cortical surface. This fact can also be qualitatively noted by visualizing the generated surface at different resolutions or without the hypercolor features, which produce over smoother surface, like the purple one. Thanks for your attention, and feel free to contact me for more information.
Thank you, Rodrigo. We appreciate you sharing your paper with us, and again, congratulations for your award. Of note, we're not going to have any Q&A during the award session, but each of the award-winning papers will be featured at one of the regular Q&A sessions that the rest of the conference papers are at. So the best paper award that Rodrigo just presented will be this afternoon in session 3A. Our next paper is the Best Paper Applications awardee. And unfortunately, we were having technical difficulties with Zhongguo presenting this live. So we're going to play the 5-minute pre-recorded video for that paper.
I'm going to present our work, 3D human pose and shape estimation through collaborative learning and multi-view model fitting. Given a single view RGB image, we would like to estimate its corresponding 3D human body. We use a simple model as our template, which is a linear function of pose and shape parameters. The shape and pose parameters can be defined by theta and beta respectively. As long as we can estimate the theta and beta correctly, we can obtain the 3D human body from simple model. Our work has 3 contributions. There are 2 categories for 3D human pose and shape estimation. The first one is called the optimization-based methods. We first extract a priori information like joint points or singulates from the image, and then a parametric model is used to fit those priori information. Another one is called regression-based methods. Deep neural network is used to regress parameters of the parametric model. Then those functions are defined to train the network. In YCB 2019, Contours proposed a method called SPIN, which combine regression and optimization in the training loop. However, they only use single-view image to train the network. In some public datasets like Human 3.6 million and MPI in 3D-HP, the videos are captured from multiple views. Therefore, we can use multi-view images to train the network. In our method, multi-view images are input of the convolutional neural network. Then, the output of CNN at pose and shape of simple models, as well as camera parameters. We can obtain the regressed simple models for each of the image and project this regressed simple models on image plans based on the regressed camera parameters. Then, using the regressed parameters as the initialization, we propose the multi-view simplify to optimize the parameters of a simple model once more time and fit the simple model to the multi-view image simultaneously. We define a new loss function based on the optimized parameters and the regressed parameters to train the network. Therefore, our method also combines regression and optimization in our training loop. For the multi-view simplify, we split the pose parameters as body orientation and joint rotation. During optimization, body orientation for the multi-view images is different, while the joint rotation for the multi-view images is the same. We define the energy function as follows. It contains joint point errors and the regularization terms. As shown in the figure, we illustrate the body orientation and its corresponding simple models on the image plan for the multi-view images. We also give the comparison of simplify and multi-view simplify. We can see that our multi-view simplify achieves the better performance, which can provide better supervision for the training of CNN. We use 3 datasets in our experiments. The first 2 datasets are used for training, and the evaluation uses all of the 3 datasets. This is a matrices for quantitative comparison. Firstly, we compare to several previous work trained by single-view image. This is the result of a Human 3.6 million. This is the result of MPI in 3D-HP, and this is the result of 3D-PW. We can see that our method achieved the best performance. Then we compare to previous work trained by multi-view images. This is a result of a Human 3.6 million. The first 4 methods know the cameras, and they don't use any parametric model. So they only estimate human pose, and the MPJPE is a corresponding reconstruct error for the Liang's method and our method. So we compare to Liang's method on the MPI in 3D-HP and 3D-PW. We can see that our method achieved the best performance. Here is quantitative results. We can see that our method also has the best performance. Thank you.
Thank you, Zhongguo. That paper will be in a QA session tomorrow evening, or Q&A session 7C. And it's paper number 1217 to help you find it. I apologize. It's tomorrow morning, session 5B, paper 839. It's getting ahead of myself. Our next presentation will be the best student paper, and Ameni Tarbelsi will be presenting that.
Hello, everyone. My name is Ameni Tarbelsi. I'm a PhD student at Colorado State University, working in the CWC lab under the supervision of Professor Ross Beveridge and Professor Nate Blanchard. And today I will be presenting our work entitled A Post-Proposal and Refinement Network for Better 6D Object Pose Estimation. Starting with a brief definition of the 6D Object Pose Estimation task. Given an input image, the task of 6D Object Pose Estimation is to estimate the Regé transformation from the object coordinate system to the camera coordinate system. The Regé transformation contains a 3D rotation R and 3D translation T. Accurate 6D object pose estimation is crucial for many real-world applications, such as autonomous driving, robot manipulation, Internet of Things, and augmented reality. However, the problem is challenging due to the variety of objects in the real world. They have different 3D shapes, and their appearances on images are affected by lighting conditions, clutter in the scene, and occlusions between objects. Furthermore, a 6D pose estimator needs to balance accuracy, robustness, and speed to be realistically deployable in real-world scenarios. In this work, we present a novel end-to-end 6D pose estimation approach from RGB inputs. In this figure, we show an overview of our two-step approach. First, the post-proposal network extends the region proposal framework to classify and regress initial estimates of the rotations and translations of objects present in the scene. Second, the pose refinement module consists of a differentiable renderer that outputs a render of the detected object using its initial pose estimate and 3D model, and a multi-attentional refinement network to further refine the initial pose estimates. Let's go a little deeper in the details of each module. This figure illustrates our 6D object pose proposal network architecture, which we call PPN. Our architecture has two stages. First, a backbone encoder extracts high-dimensional region feature representations from the input image. Second, the extracted features are decoded by 3 parallel convolutional blocks. Block A is a rotation proposal network that regresses a 4-dimensional quaternion vector for each image region and object class. Block B is a translation proposal network that regresses the translation components. And Block C is an object center proposal network which returns high-class confidence in regions where the object center is present and low-class confidence in regions where it's not. After the inference of object center detection and pose estimation, which is done by one pass through PPN, we apply non-maximal suppression to eliminate duplicated predictions when multiple cells have high confidence scores for the same object. Our proposed multi-attentional refinement network, MARN, iteratively corrects the 6D pose estimation error returned from PPN. First, 2 color crops are used. The rendered crop is generated by rendering the 3D object model viewed according to the predicted pose. The RGB crop is generated from the original input image using the predicted pose with an additional offset to account for pose prediction error. MARN's feature extraction block is composed of 1. A shared visual feature embedding network that captures visual features of the object, and 2. A flow estimation network that estimates the object motion between the rendered image and the observed image. Then, the visual feature map extracted from the rendered crop is warped toward the visual feature map of the image crop guided by the flow information. Furthermore, the estimated optical flow is concatenated with the feature map extracted from the image crop. MARN integrates the spatial multi-attention block. This block aims to localize discriminative parts of the target object with spatial multi-attentional maps. First, we extract the attention maps, and then we element-wisely multiply them with the feature map to extract the attentional feature map. Finally, the residual pose estimation block processes the residual pose estimation using convolutional operations followed by fully connected layers. The different components of our approach are trained jointly in an end-to-end fashion with a multitask learning objective L total. For the PPN pose and refiner loss, we use the average distance between the key points projections of the 3D model using the predicted pose and the target pose. For the confidence loss, we use a simple L2 distance, and L orthogonal is a regularization term used to discourage multiple attention maps locating the same discriminative object path. The regularization emphasizes orthogonality among the attention maps. Our pose estimation models are compared against other RGB-based methods across 3 commonly used datasets: YCB-Video, line mod, and line mod occlusion. As shown in the 3 tables, our method obtains the best results on all datasets. More specifically, on the occlusion and YCB-Video datasets, which are considered more challenging due to the variety of objects present in the scene and the high level of occlusion. The significant improvement in performance shows the effectiveness of the different components of our model in robustly recovering the poses of objects under severe conditions. We performed an ablation study on MARN's components to measure the effectiveness of each of its components. In all, we test 4 variants. First, we remove the flow features and attention maps. Second, we only remove the attention maps. And third, we experiment with one single attention map. Finally, we compare with the 3 variants with the complete MARN architecture in variant 4, and we show the importance of the different components of MARN in the performance of our model. We compare PPN with state-of-the-art methods that do not use refinement. We recall that PPN is the first module of our pipeline that regresses object pose proposals in a single shot. Unlike these approaches, PPN has the highest speed, which is 50 frames per second, is completely end-to-end, and does not require any additional steps such as PNP algorithm. Thus, we suggest that PPN alone is fast and robust enough to be deployed in real-world applications. As a conclusion, we proposed an end-to-end 60 pose estimation approach that performs a state-of-the-art RGB-based methods on 3 commonly used benchmarks. First, we introduced a post-proposal network, PPN, that is fully CNN-based, yielding fast and accurate pose estimations in a single pass from RGB images without additional steps such as PNP algorithm. Second, we introduced a pose refinement network, MARN, that uses a hybrid intermediate representation of the input image and the initial pose estimation by combining visual and flow features to learn an accurate transformation between the predicted pose and the actual observed pose. And finally, we introduced the integration of a spatial multi-attentional block that highlights important feature parts, making the refinement process more robust to noise and occlusion. Thank you.
Thank you, Ameni. We appreciate you sharing with us your paper again. Ameni's paper, Pose Proposal and Refinement Network for Better 60-Object Pose Estimation, was the best student paper. She'll be presenting the Q&A portion of that tomorrow evening in oral session 7A, and her paper number is 1274. Our next paper will be presented by Rushil Anirudh. The paper is Generative Patch Priors for Practical Compressive Image Recovery, and this is the best paper, honorable mention.
Thanks, Ryan. Good morning, everybody. I'm Rushil Anirudh from Lawrence Livermore National Labs, and this paper is a joint collaboration with Suhas Lohit from Mitsubishi Electric Research Labs and Pawan Turaga from Arizona State University. First of all, I'd really like to thank the WACV organizers and the awards committee for considering us for this award and for actually giving us the award. I'd also like to thank the anonymous reviewers and the ACs for recognizing the work and championing it. Our paper proposes a new kind of a generative prior for inverse problems, and we focus on the specific application of compressive sensing. The central idea of our paper is to represent images with patch-based generative adversarial networks, or GANs. This is related to a line of work that has become quite popular in the last few years called GAN priors, which have been shown to be successful for all kinds of inverse problems. Essentially, the idea being that you want to restrict the solution to the inverse problem to be the output of the GAN, the generator, which is already pre-trained on some data set. The problem, though, is that this approach doesn't actually generalize when your inverse problem is dealing with a domain that's outside of what your GAN has been trained on. So, for example, say that you have a very nice GAN that has been trained on human faces, but your inverse problem is actually on cars or animals. This doesn't work. And not only for different objects, it doesn't also work when you have different aspect ratios, different sizes, resolutions, and et cetera, et cetera. So while the idea is extremely interesting, it's limited by its practical application. To address this issue, we propose the generative patch prior, or GPP, which essentially relaxes this idea of the GAN prior by restricting the individual patches to be from the pre-trained GAN. That is, instead of saying that the entire image should be from the GAN, we just say that the individual patches in the image should be from the GAN. As a result of this is that GPP can now be used to represent any natural image using an appropriate patch composition function. That is, as long as we know how to combine a set of patches into an image, we're able to use GPP to solve inverse problems with any natural image. The other advantage is that the patch manifold itself is actually much simpler to learn than the image manifold. Right, and this is evidenced by the fact that there's no single unconditional GAN today which can represent the richness and the diversity of the entire image manifold even at a fixed resolution, even at a fixed aspect ratio, and so on. Right? And the patch manifold, on the other hand, is much simpler to train. So here we show an example that is in the paper where we take a GAN that is pre-trained on CFAR32, the popular image classification dataset, CFAR, where the images are of size 32 by 32. And we use that pre-trained GAN to recover an image that is of size 1536 by 1024. The size is not important, but it's basically a non-standard size, and it's a non-standard aspect ratio. And clearly, the GAN that we've trained on has never seen this particular image. And what I'm showing you here is basically the optimization process and how it proceeds. Every tiny square here is an image that is generated by this pre-trained GAN. Right? And as we initialize randomly, and as the optimization proceeds, you can see that we end up getting a very high quality solution for the ground truth image, which is shown on the right. This is with only 10% measurements in compressive sensing. So let's look at the optimization process in a little bit more detail. We particularly consider the problem of patch-based compressive sensing, which is basically the idea that we break down a scene into a set of patches, and each patch is individually measured or sensed with the same measurement operator phi. And the ground truth is obviously unknown. And as I mentioned previously, we start with basically creating a random set of patches and organizing them into the size of the image that we expect to see. We then compare every single patch with the measurement that we actually observe when projected through the measurement matrix, and we compute a loss. We want to minimize this loss by updating points in the latent space. We use gradients and update points in the latent space so that we can update our estimate of the patch. This is exactly the same optimization problem that is used in GAN priors, in generative priors out there, called projected gradient descent. And once we let the optimization run, we see that we're able to recover extremely high quality solutions by just placing this loss at a patch level. It's interesting to note that we are only placing a loss at individual patches. We don't actually place any kind of consistency across patches within the same image. And yet, what we see is that this loss is sufficient for us to actually recover this consistent, nice-looking, realistic image. Again, keep in mind, this is a GAN that has been trained on CFAR32, right? CFAR-C images, which is of size 32 by 32. So if you want to look at how GPP compares with other existing priors, we look at two quantities mainly. One is the generalizability and one is efficiency. Generalizability on the y-axis is basically how broadly applicable that particular prior is. So if you're somewhere below here, you're maybe only applicable to specific image distributions, whereas if you're somewhere on top, you're applicable to any natural image. Efficiency is the property of the quality of the recovered image under very few observations. Now, classical methods like total variation are way up here because they are basically applicable to any natural image, but they tend to be less efficient and they give us poor reconstructions when you have very few observations. More recent advancements have improved on that, like the deep image prior, which are also applicable to any image because you essentially overfit a neural network to a particular image, but they also tend to be not as efficient as we want. GAN priors, on the other hand, are extremely efficient, but they're hardly generalizable. We know this because even with very few observations, we can get very high quality solutions as long as we know that we're in that same distribution on which the GAN has been trained. GPP, interestingly, occupies this kind of sweet spot. It's much more efficient than your classical priors, and it's much more generalizable than GAN priors. It can be applied to any natural image, and it also has a lot more efficiency and higher quality reconstructions when we have very few observations. So in some sense, it's more practically applicable for the real world. We see this in quantitative experiments where both for 10% and 1% measurement rates, we see that GPP outperforms several state-of-the-art methods. Of particular note is the reconstruction qualities that we obtain at just 1% measurements, which are several dB higher than any of the other competing methods. So we see that this notion of using a pre-trained patch GAN actually gives us a very good boost in performance. In the paper, we also study how GPP can be used with physical hardware, compressive cameras. The problem with physical compressive cameras is that they can suffer from all kinds of environmental distortions and environmental changes like sensor drift or sensor gain. As a result, the measurement matrix and the effective measurement matrix that we have in the hardware can be different from the one that we have designed, right? And the change can be in some unknown fashion. Now, this kind of causes an inconsistency because there is the measurements that we actually observe don't actually align with the measurement matrix that we have designed. The usual standard way to correct this is by manual calibration, which is obviously expensive and impractical, especially if it has to be done in a day-to-day basis. So we use the idea of this notion of self-calibration, which is known in compressive sensing. We use a very simple linear model where we say that the new measurement matrix phi hat is nothing but a phi plus b, where a and b are just two scalars, which are unknown. Now, this is a simple linear system which can be solved in closed form if we know the ground truth, the solution for the inverse problem. But since that is also unknown, we end up solving it using an expectation maximization approach in an alternating fashion. So we get updates for a and b, and then we use that for the best update on x, and so on and so forth. In synthetic experiments, we see that this works really well. So when we use arbitrary values for a and b here, as shown here, we see that the values converge to the ground truth values even as they are unknown. And simultaneously, we're also able to estimate very high quality reconstructions for 10% measurements and 1% measurements and so on. The most interesting aspect about this is that even this simple measurement model, simple calibration model, that is when combined with GPP, can recover very good solutions from uncalibrated measurements of a real data set. So we've taken measurements from a physical compressive camera that has not been calibrated, and we just directly give it to GPP with self-calibration, and we see that we're able to do really well and actually recover high-quality solutions while automatically also estimating so keep in mind here, we don't know what the true calibration model is because this is a real-world setting. So we're able to recover it much better than many state-of-the-art techniques. So in the paper, we go into a lot more detail about the properties of GPP and how it compares to the GAN priors and tradition in general, and we do a lot more analysis, which may be of interest to you. We've also released our code and models on GitHub. So if you have any questions, please feel free to reach out to us. I look forward to talking to many of you in the coming days. Thank you so much.
Thank you very much, Rushil. So Rushil's paper will be in tomorrow afternoon's evening session 7C. The paper number is 1217. Our final awardee presentation will be presented by Wenhu Chen. The paper is titled Metamodule Network for Compositional Visual Reasoning. And we'll turn the time over to Wenhu.
Hi, everyone. Happy New Year. My name is Wenhu Chen. I'm from UC Santa Barbara. Today, I'm going to present my paper on Metamodule Network for Compositional Visual Reasoning. This is a joint work between UC Santa Barbara and Microsoft. So first of all, I want to thank the reviewers and committees for recognizing the work. I'm really honored to receive this award. So let's get started. So the problem we're going to solve today is called visual question answering, where the AI system will need to answer a question by grounding on the image to find the answer. To solve this problem, there are mainly two types of neural network. One is called the monolithic network, and the other is called the module network. So for the monolithic network, it will use our unified neural network architecture to answer all the questions in the given data set. While for the neural module network, it will try to synthesize the instance-wise neural network for each and different questions in the data set. So for the monolithic network, it's very scalable and generalizable because it doesn't require any hand engineering to define any modules. For the neural module network, it's very explainable and compositional. So today, we're going to propose this metamodule network to combine the merits from both sides. So let me first talk about the scalability and generalization issue for the neural module network. So in the neural network, module network, we need to define a specific network for different functions using neural modules. And this is not very scalable to more complex scenarios. Let's say if we are going to dealing with 50 different functions, it's very expensive to hand design all these different 50 different neural networks. And the other thing is the generalization issue. If during the training time, we are not training the model to learn certain module, we cannot generalize them into the test time. So which means that the model cannot infer some new functions during the test time. So in order to solve this problem, we propose this metamodule network. So this is the basic concept. We have a function instruction. Let's say we want the module to perform the function of locate left, and then we will put this function instruction to a function factory. And this function factory will produce a meta-module network. And then for this module network, if it receives an image, it can find out what's on the left-hand side to do this object detection. So the core problem here for the meta-module network is called instantiation, where we have a template neural network which has 4 different pods. So one of the pods will take in the function embedding from the function description, and this can be instantiated into a functional module to perform a certain task. So this functional module will take in an input vector and then output another vector. Besides this input-output, the functional module is also able to produce an attention map over the image to explain its decision-making. So this is how we do the compositional reasoning in the meta-module network. So we first pass this question into a semantic graph. So here, we have a tree structure here for this question. And then we will run the instantiation procedure for each and every node in this semantic parse tree to get our module network. So this module network will receive the input image and do some compositional reasoning, and then finally get the answer. So how to train this meta-module network? There are basically 2 kinds of supervision. So this first supervision is module level supervision. So in this module supervision, we first pass the question into the semantic parse and then run the different functions on the image to get the oracle attention map on the image. So on the other end, we also have this module network. We will find this corresponding module and then let it output the attention map. So we will minimize the discrepancy between the oracle attention map and the model produced attention map to make sure that each of the module is performing the functionality that it's supposed to perform. Besides that, we will also have this canonical cross-entropy loss function to minimize the loss of answering a certain question. So during the training time, we will plus these 2 loss functions and jointly minimize the function. So in order to evaluate our model, we choose this GQA dataset because it consists of lots of complex questions requiring very complex semantic parses, and also the GQA dataset requires a very large functional inventory consisting of roughly 40 different functions. So it's a very good benchmark to test the scalability of our model. So we mainly compare with module network and monolithic network. As you can see, our model can significantly outperform both of these 2 models. So on the other hand, we also test the generalization of capability of our meta-module network. So what we did is that we tried to held out some of the functions from the GQA dataset and to see if our model can generalize to these functions during the test time. So here we compare with the neural module network. As you can see, the neural module network is basically doing random guess and cannot generalize to the test time. While our model can generalize to these unseen functions reasonably well on different functions, so which means that our model has better generalization ability. So this is a conclusion. We combine the meta-learning with neural module network to propose this meta-module network. And this meta-module network is more scalable and generalizable than the neural module network. And the meta-module network is also more explainable than monolithic network. And that's it for the talk. Thanks everyone for attending.
Hi, everyone. Thank you, Wenu. I would like to real quick just show a slide that shows the oral sessions for Q&A for each of the award-winning papers. You can find them on the main conference website in each of these respective sessions with the paper numbers that are indicated. And again, the first 2 are the best papers for the algorithms and applications track, respectively. The third one is the best student paper, followed by honorable mention for best paper and best student paper. I'd like to thank all 5 of our presenters during this session. I want to congratulate all of them on the awards that they have respectively received. They had excellent papers, and want to thank all those papers award authors from the conference. We look forward to seeing and hearing from many of them during the Q&A sessions through the balance of the conference. So one more thing really quickly. Next year's conference, as Kevin mentioned, is going to be, hopefully, we're almost certain it's going to be in person. And we have the same organizers, same general chairs, Gerard and Kevin, and then same program chairs, myself, Christian, Laura, and Jingyi. And we look forward to welcoming you in Waikoloa, Hawaii next year. Hope all of you will be able to attend in person. We have a few minutes now before the keynote will start, about 10 minutes. Just really quick to orient you, the way that the conference is organized this year, we're going to take a short break and start right at 9 a.m. local time Pacific. But we have two sort of blocks of sessions each day. So today, tomorrow, and Friday, there's a 8 a.m. to 11 a.m. Pacific time block of sessions. And this morning we have our first keynote. And Gerard Medioni will introduce our speaker in about 10 minutes. And then there's a second block of sessions in the afternoon/evening from 5 to 8 p.m. Pacific time. And this is in part to facilitate our worldwide audience. We're not all co-located, and so to help our participants attend at least one, if not both of the sessions, they're spread out significantly. So please see the conference website for details about which papers and which sessions, but we hope that you'll enjoy the conference. And we're very excited to have you and look forward to interacting with you throughout the conference. Thank you.